Here's the fourth section in Chapter 7 in our physics book. The chapter is about energy, and now we're going to talk about mechanical energy, which we label as either being kinetic energy or potential energy. And this is a natural outgrowth. We've talked about work and power, and just to give you a hint, coming forward, we're going to talk about how work and energy are related, ending up with the conservation of energy. You've already talked about the conservation of momentum, and the same will hold true for energy. And then we'll end up looking at machines and how we measure energy. So when we look at the mechanical energy of an object in motion, we're looking either at the energy that's due to its position, its potential, its motion, its kinetic, or both. So when it's in movement, we talk about its kinetic energy, and when it's in position, we talk about it having potential energy. Think about the mass on the end of a pendulum. When it's at the heights and going to land, or yourself at the top of a roller coaster, there's potential. You know that there's going to be movement, kinetic energy following. When we talk about potential energy, and this is one where the physics word pretty much matches the ordinary language word. Potential energy is energy that is just ready to come out. It's stored, it is ready, and it's going to do some work for us. A couple examples: when we stretch the bow in a bow and arrow, when we stretch the rubber band in a slingshot, or when we hold something at a height ready to drop it. Those are things, that's movement that is imminent. The biggest one, we've got gravitational potential energy, and that is when we elevate something. So either water in a reservoir, the raised ram in a pile driver, your rock at the top of a cliff, it's ready to do something. Gravitational energy is the gravitational position is a special case of potential energy. Remember, when we measure energy, it's going to be the work, it's equivalent to the work done. Potential energy, we can calculate it, the mass times the acceleration due to gravity times the height. And our equation is right there. And the work is, work needs to be done on an object to put it into a position such that it has potential energy. We have to move it up to its height so that it's got potential energy to drop down toward us again. So when your car is in for an oil change and it gets hoisted up in the air, does it have potential energy relative to the floor? There's your question. Do we have enough information to answer this? Or is this something that varies? Or is this something that you can answer yes, no, right at this point? Does an elevated car have any potential energy? Well, the answer to this is yes. And it is because it could be released and fall due to gravity. Here's something that is really important to think about relative to looking at simple machines that we're going to do next, is that the potential energy strictly has to do with its height of elevation. Okay, so all three of these situations have the same potential energy because of the fact that they are all 3 meters above the base. Now, that might be a little bit odd to you. You might say, gosh, the distance that was taken to get to these places is much further than the distance here, but also it's counteracted by the fact that your push to get the ball, that 10 Newton ball up there, the push to take it to this elevation is less in these two situations. The push to take it straight up would be a bigger force. And remember that your work, remember the relationship for work is force times distance. Or so the energy is the same. The potential energy is the same because it is based on the height. Contrast that with kinetic energy. Up till now, we've been looking at potential energy. Now we're going to look at kinetic energy. Remember that the prefix "kena" means to move. So anytime you've got some variation of the word kinetic, there's movement involved. And kinetic energy is the energy of motion. The energy is a relationship on an object's mass, and not just its speed, but we square the speed. So there's a proportional constant of 1/2, and your equation, the thing that you'll need to remember, is that kinetic energy is the mass times the speed squared, so you multiply it by the speed again, divided by 2. The relationship that this is showing you is we're no longer linear, and if we have the case where the speed is doubled, then the energy is quadrupled. So here's your question, and it's this is a vocabulary question as much as anything. When a car has momentum, does it also have energy? Well, to have momentum, momentum has a velocity component. So if there's no velocity, if there's no speed, you have no momentum. When a car has momentum, does that also mean that it has kinetic energy? Does acceleration come into account? The fact that it's a scalar or a vector? Or do we say that there's simply no relationship? Well, the answer here is that car with motion does have kinetic energy. It's got momentum, it's got motion. Because it has motion, it has kinetic energy. Now you've been working so hard on it, and the idea that something is a scalar or a vector doesn't matter right now. If it's moving, it has momentum and kinetic energy. Those are related. Here's your equation to remember. Kinetic energy is either the force times the distance or 1/2 the mass times the speed squared. We can also look at it as being equivalent to the work necessary to bring the object from rest to its speed.